Welcome back. Today we're going to be talking about this series here, which is the series from n equals 1 to infinity of 2n to the third plus 7 over n to the fourth sine squared of n. So we were asked, does it converge or does it diverge? And you look at this and you're like, oh my god, it's hell on earth. Here's a simple strategy you can use to solve these series. Now, when you need to understand convergence or divergence, first you do a divergence test. I'm going to notice that this is going to simplify to 0. And if you don't see it, notice how we have a power of 3, a power of 4. If I keep taking the derivative of this, we're going to notice that this power is going to stay while this power is going to go 2, then 2, then 1, then just a constant. And that's going to give us some constant of blah, blah, blah over infinity, because we're going to keep n here because if we just even had n to the fourth is going to go n to the fourth, n to the third, n to the second, n to the first, and then constant. That's one more step than n to the third. So we know that this divergence test will read 0. And we know that if the divergence test gives us an output of 0, well then that's gonna be indeterminate. We do not know if it diverges or converges. If we got a value, we know it'd be divergent, because we know that every time in the sequence when we get to infinity, we're adding something that's constant. We're adding a constant value basically. Every single term, which means it grows to infinity if we have infinite terms in our series. So divergence test doesn't work. It's indeterminate. Does it diverge or converge? I don't know. Here's a simple step you can do. This is the comparison test, and that's what this problem is based on. If you're watching this video, you know that you're looking for the convergence test. Here is how we use a convergence test for when we have a bunch of junk. Notice anything that will be a constant value or something that is between an interval of a constant value. 7 is constant, okay? We're multiplying it by 7. Sine squared is an interesting thing because it's going to oscillate between 0 and 1. It's a sine function. It goes like this. Okay? Forever and ever and ever and ever and ever. So whatever you multiply it by can never exceed the amplitudes of 0 and 1. And if you don't believe me, plug it into a graphing calculator, look at the amplitudes. You're going to have 1 and 0. It will never diverge out of that range of intervals, right? We're multiplying it by a factor of n to the fourth. Alrighty, so we're going to look at it more so as, we're going to look at the behavior of the divergence more as 2n to the third over n to the fourth. Okay, we'll compare that to our parent series, which is 2n to the third plus 7 over n to the fourth sine squared to the n. Okay? So basically what we did here is we took out all the junk that we don't really know how to, say, do an integral test for and all this stuff. We're going to make it into a simpler series here. This will simplify into 2 over n, all right, and we'll take the series of that. We know that this will be divergent because this is a harmonic series, and all harmonic series diverge. Okay, we plug in infinity here. Infinity. Okay, so we determined that this is divergent, but we need to make a comparison between this before we can definitively say it's going to follow divergence or convergence. So we're adding to our numerator, we're growing the value, but here we're adding sine to the bottom, we're making this denominator smaller, because if this value is 1 to 0, well, that's not really how you write an interval, but if we're plugging values 1 to 0 in here, we're inputting values, we're outputting 1 to 0. If we get anything less than 1, I want you to notice that it's going to grow our numerator. So we're plugging in like 1 here, okay, or 2, or 3, or 4. And then we're multiplying it by some factor that's going to shrink it. That's going to make the denominator less, which is going to make the overall value greater. So we're going to say that this is greater than this. Okay? Alrighty, so what does that actually say about our function, or if we looked at these as functions? I don't really care what they're doing, but let's just say that this, we'll graph this one first. Let's just say that it's following this growth. It could or could not be doing that, but let's just say that it is. Okay, so it's the green and it's diverging. Well, if this is greater than it, always, is it going to be able to cross this boundary? Is it going to be able to say do this? It can never cross green, because if this inequality is true, then this is not possible. Therefore, if this series converges, diverges, then this series must also diverge. That's the thinking that you need to have. If this series diverges, because it simplifies to a harmonic series that diverges, well, then our parent series, granted it's greater than always, must also diverge. That's how you solve this. So if you want to write out a formal answer to this problem in a way that your professor would probably appreciate, what you're going to say is, because 2n to the third over n to the fourth, that series is harmonic, thus divergent, and our parent series and this is greater than our sister series that we've made, then so because this is harmonic and thus divergent, and this is true, then our parent series is also divergent. So that's how I went about solving this. I said, okay, I'm going to pick a function. I'm going to see if maybe it makes this scenario where it either, it kind of it's called a squeeze theorem. It's going to push our series up, and it's going to allow us to make a comparison by this harmonic series here. So we say, because this series is harmonic, thus divergent, and we know that our parent series is greater than our sister series, well, then we know that our parent series is divergent. This is the comparison test. Hope you guys enjoyed my rationale and thinking. If you did, please drop a like, comment, and subscribe. I would greatly appreciate it. I'm trying to get this out to as many calculus students as I can. Have a wonderful day.